Attendance direct बस नहीं करते attendance direct बस बरोबर
ते एक हे आसा डाउनलोड करचें पडटा
ऍप डाउनलोड करून दे
एप न्हू थंयच लॅपटॉपार जाता ते
हां
लॅपटॉपार करपाचें जाणा तूं ते when you go for this only ते when before opening joining,
Okay.
there's some provision there.
In Jimmy only.
Go.
Jimmy open करून माहिती आहे
Check. Yeah, automatic logging. Automatic, I don't know how to do it.
ते ऑटोमॅटिक घेतलं.
Automatic जाता
त्याची
पण.
नाव फिट करून असतं
ना काय ना. ते हे धाडलें न्हू तेंका.
लिंक धाडले.
When this thing is slideshow is going on, it doesn't happen.
Then you have to do so.
And attendance मागीर automatically येता. Save that. And you can save also.
इंगाच बदल म्हणजे डायरेक्ट इंगा करून माहिती सेव्ह आहे डायरेक्ट.
PJ.
When you click on this list.
List येता. Okay. That also you can do. That also you can do. Good morning, students. Good morning, students.
Good morning.
Good morning. Okay,
Good
I'll
morning,
start
sir.
here. I'll start with the lecture. Now, so far in Einstein's theory of relativity, we have studied under the special theory of relativity what is called as contraction of the length, dilation of the time, and Doppler's effect. In the contraction of the length, hello? In the contraction of the length, when the body is moving and the length of that body is less than please mute the mic.
Hello.
Hello. Please mute the mic. Okay, we'll continue now. So, in the contraction, length contraction, the length of the moving body is found to be less than the length of the body when it is at rest. In the time dilation, the time interval measured in the motion is is more than time which is measured when it is at rest. That is called as a time dilation. Then we also seen the Doppler's effect of the light. Remember that all these phenomena are when the body is moving with very high speed. Now that one more concept we'll take is the mass. In the Newton's relativity, mass is an absolute quantity. Mass is an absolute quantity means it does not depend upon frame of reference. Whether the body is moving or at the rest, the mass is constant. Value of the mass is constant. That is in the Newtonian relativity. But Einstein showed that the mass of the body also depends on the velocity. The higher the velocity, the larger is the mass. So that means mass of the body is not absolute, but it is relative. It depends upon frame of reference. Now mathematically we will find the relation between mass of the body when it is moving with some velocity and mass of the body when it is at rest. Now we consider the two frames as we have taken earlier. One frame is frame S, other frame is frame S dash. With our regular notation, the second frame is moving with respect to first frame with the velocity v. Second frame is going away from the first frame with the velocity v. Then we consider a mass, a body of some mass in the second frame. It is in the second frame and it is moving with the velocity w with respect to the second frame. So in fact, that mass is a third frame of reference. Although we are not mentioning it here, it is a third frame of reference. So in fact, v is the velocity of the second frame with respect to first frame. W is the velocity of the third frame with respect to the second frame. Now, we take one more mass, identical mass, another identical mass, moving with the same velocity with respect to the second frame in opposite direction. So we don't call it as a fourth frame, but it is a third frame moving in the opposite direction. So since it is moving in the opposite direction, the velocity is w. So this w and minus w are the velocities of this body with respect to the frame S dash. Now with respect to the frame S, then we denote it by the symbol u. Now, see this for the second frame, both the bodies are moving. They are moving towards each other with the velocity w and minus w. So then what happened? Since they are moving towards each other, after some time they will collide. Since they are of the equal mass, moving with equal velocity, they will collide and they will come to rest in the second frame. So when they collide, afterwards, these two bodies will move with the velocity v. So it comes to rest in the second frame. They move with the velocity v with respect to the first frame. Then to this, we'll apply conservation of the linear momentum. Conservation of the linear momentum means the total momentum before the collision is equal to total momentum after the collision. Because here, before the collision, they are moving towards each other. After collision, they will move together because the velocities are equal but in opposite direction and mass is also equal. So they will move, they will come to rest in respect to the second frame, but with respect to first frame, they will move because second frame is also moving. So the total momentum before the collision is equal to total momentum after the collision. Now, so for the frame S, see for the frame S, the mass of this body, first body is m1, mass of the second body is m2. See, they are not same because now they are in the different frame. So m1 is the mass of the first body, m2 is the mass of the second body. But actually, in the frame S dash, both of them had the same mass. So then velocity with respect to first frame is u1 and u2. That is what the u is a symbol which is used. The velocity of the third frame with respect to the first frame. So for the frame S, so you are doing this now measurement from the frame S. The total momentum before the collision is m1 u1 plus m2 u2. After the collision, see, they stick together and they move in the second frame. In the second frame, they come to rest. In the first frame, they move with the velocity v, because they come in rest in the second frame. So velocity of them will be same. Mass is m1, velocity is v. Mass is m2, velocity is v. So this is from for a frame S. We use the conservation of the linear momentum. Total momentum before the collision is equal to total momentum after the collision. Then this is what we have considered. Now we will simplify. Now we want to find out the relation between the mass measured when it is at rest and when it is moving. The relation we have to find out. So now we will simplify this. What we have, that conservation of linear momentum, we will simplify. So we divide by m2 throughout. So this becomes m1 by m2 u1, and m2 m2 cancels u2, m1 by m2 v, m2 m2 cancels, so plus v. Then we bring this m1 m2 and m1 m2 together. So on this side when it comes minus sign, and this u2 is taken on the other side, is v minus u2. So when we take the common, m1 by m2 is u1 minus v equal to v minus u2. So m1 by m2 equal to v minus u2 divided by u1 minus v. So this is the equation 1. So we get the mass ratio of the masses of the two bodies. Now we have to evaluate this. To do that, say, we use the Einstein's law of velocity addition. Einstein's law of velocity addition. And the formula was for u equal to v plus w by 1 plus vw by c square. So there are three frames. The second frame was moving with the first frame with the velocity v. Third frame was moving with respect to first frame. Second frame velocity w. And the third frame was moving with respect to first frame. The symbol was u. So u equal to v plus w by 1 plus vw by c square. Now in this case, for a first body, it is moving with the velocity u1 with respect to the first frame. Then that second frame is moving with the velocity v, and the third frame is that first body moving with the velocity w. So you write u1 equal to v plus w by 1 plus vw by c square. For a second body, see, second body is moving with the velocity minus w, because with respect to second frame, it is moving in the direction opposite to the standard one. So that w is replaced by minus w, and with respect to first frame, that the body is moving with the velocity u2. It will be different velocity, different from the first one, because it depends upon the frame of reference. So u2 equal to v minus w by 1 minus vw by c square. We substitute this u1 and u2. See, u1 and u2 we substitute in the equation 1. So this quantity u1 and u2. So in substituting the equation 1, we get like this. And when you simplify, see, when you simplify, you get m1 by m2 equal to 1 plus vw by c square divided 1 minus vw by c square. Again, we have to simplify this. So m1 by m2 we have to simplify. Okay. Especially we want to find out here that 1 minus vw by c square and 1 plus vw by c square. That is what we want to find out. To find that, we will consider this root of 1 minus u1 square by c square, because I know in advance that it will be related with that 1 plus vw by c square and 1 minus vw by c square. So we take root of 1 minus u1 square by c square. So here 1 minus 1 by c square, u1 we substitute, that Einstein's law of addition, we substitute there, this, and then this c square will take in this numerator inside, so it becomes c whole square. Then we take the LCM here, and then either you can use here x square minus y square is equal to x plus y into x minus y, or you can expand this. Each term you expand, a plus b whole square. Here you expand this. This also you expand, v by c plus w by c whole square. And when you expand this, you will get it. The square root of a square is same thing. So we have expanded here. 1 plus vw by c square whole square, that is 1 plus 2, 1 into vw by c square plus v square w square by c raised to 4. Similarly, this v by c plus w by c, that we have expanded, and we get this here. Then this what we have done, and now here the especially this term will cancel, second term and here second term, that will get cancelled, and when you take that w square by c square outside, you get this term. And then say it is root of the 1 plus vw by c square is there in the denominator. In the numerator, root of 1 minus v square by c square minus w square by c square, 1 minus v square by c square. Then this is common, and when you take this common, 1 minus v square by c square, what remains inside is 1 minus w square by c square. This is what we get. Then further, we want to get this. Say we wanted to get 1 plus vw by c square in that expression for m1 by m2. So we take it here, and this is taken in the denominator. So 1 plus vw by c square is what we wanted, because we want to substitute in that equation for m1 by m2. We get this. Now similarly, one can show that we also wanted 1 minus vw by c square. We can show that 1 minus vw by c square. So here you get the similar thing, only instead of u1, what you will get is u2. So we found this, and we will substitute in the equation for m1 by m2. So m1 by m2 was the equation 2 is like this. We substitute here 1 plus vw by c square as root of 1 minus u2 square by c square. Then 1 minus vw by c square is root of 1 minus u1 square by c square. Then we cross multiply. m1 root of 1 minus u1 square by c square equal to m2 root of 1 minus u2 square by c square. Now it is like say m1 root of 1 minus u1 square by c square equal to m2 root of 1 minus u2 square by c square. Suppose third body is there, then it will be m3 root of 1 minus u3 square by c square. So the product will be constant. See, product of the mass and into the similar quantity, that will be constant. Then suppose the body is at rest in the with respect to first frame, we call that mass as m0, body at rest. Body at rest with respect to the first frame, that means u will be equal to 0. So what you get is root of 1 minus 0 by c square, and that is equal to m0. Now this m0 is called as the rest mass. Rest mass means when it is rest, it will have some mass. Say this equation shows that when it is rest, it will have some mass. If it is moving with the velocity u1, it will have mass m1. If it is moving the velocity u2, then it will have the mass m2. Okay. So in general, we will say that m is the mass of the body when it is moving the velocity v. Then we can write. So now we generalize. See, this is equal to m0. So if the m is the mass of the body when it is moving the velocity v, so we put here m, instead of u we put v. So m root of 1 minus v square by c square equal to m0. So m equal to m0 divided by root of 1 minus v square by c square. So that means if the body is moving the velocity v, the mass is not m0, but see this denominator, it is less than 1. So quantity will become more, m will be greater than m0. So when the body is at rest, it has the minimum mass. If it starts moving with certain velocity v, then its mass will be higher. So from this equation we see that m is greater than m0. So this equation tells us that according to the Einstein's theory of relativity, the mass of the body is not absolute. It depends upon the frame of reference. That means when it is at rest, it will have some mass. If it is moving, it will have the higher mass. Okay, so this is also very important formula. M equal to m naught divided by root of 1 minus v square by c square. So this is the formula for the relative mass. It is called as, m is called the relativistic mass. M naught is called as the mass of the body when it is at rest, where m is called as the relativistic mass. Relativistic mass means the mass of the body when it is moving. So according to theory of relativity, the value will be different, value will be higher. Now because of that, since the Newtonian relativity, mass is the absolute. In the Einstein's theory of relativity, mass is not absolute, but mass is relative. Mass is relative. So mass is relative means mass depends upon the frame of reference. Similarly, see the momentum. See when the momentum is there, actually the Newton's theory of relativity, momentum is mass into velocity. Mass is constant. So momentum depends upon the velocity. But here in the Einstein theory of relativity, mass is also not constant. Mass also is variable. So velocity is varying, the mass will also vary, and that momentum is called as a relativistic momentum. Similarly, the force is also relativistic. So when the body is moving, the force acting will be also different. This is the force is rate of change of moment. Newton's second law. The force is rate of change of momentum. And that is equal to the rate of d by dt of m into v. But here m is also variable. So d by dt of m naught by root of 1 minus v square by c square into v. So this force is also relativistic. So when the body is moving, the form of the Newton's law will remain same, but the value of the force will not be same, because basically what changes is the mass. So this is about what is called as the relativistic momentum and relativistic mass. So I'll go to the next topic. See, the next topic is chapter number 3. See, chapter number 3. The chapter number 2 was relativistic kinematics. See, relativistic kinematics. Now, the chapter 3 is relativistic dynamics. So, I already told you the difference between kinematics and dynamics. In kinematics, you don't have to take into account the force, because see, we are dealing with the inertial frame of reference. And basically, we are dealing with the velocity. And when we deal with the velocity, you don't have to consider the force into account, because it is the inertial frame of reference. The velocity remains same. Either it is at rest or it is in uniform motion. So the no force is acting. Since no force is acting, you don't have to take into account the force. So that study is called as a kinematic. In relativistic dynamics, you have to consider the force into account, because in this chapter we are finding the another important equation, what is called as the E equal to mc square. So E equal to mc square. This is also another famous relation given by the Einstein using a theory of relativity. So it deals with the energy. So it deals with the energy. So it will deal with the kinetic energy. And when you deal with the kinetic energy, we are dealing with the work done. And when you deal with the work done, what will come there is the force. So force you have to consider. So that's why this chapter is named as relativistic dynamics. So let us try to find out the relation between mass and energy. That is what we will show. E equal to mc square. We have used this. You might have used it in many places. E equal to mc square. But how it is derived, that is what we are going to see. Suppose a particle is at rest. Now we have already seen in the previous chapter If the particle is at rest, it will have the minimum mass. When it is moving, the mass will be different. And the mass, when it is at rest, is called the rest mass, m naught. Now, this mass is acted upon by the force. So it is acted upon by the force. So when it is acted upon by force, it may start moving. It will get accelerated. It may be get accelerated or it may get deaccelerated, depending upon in which direction the force is applied. And the body will move through the distance x in a time t. So work will be done. So work, see, the force is acting. So now what happens? The body at rest, you are exerting the force. So now the body starts moving, and during that time a work is done. Now when you apply the force, work is done because force is there, displacement is there, but consequence of that the body starts moving. So that work done is converted into kinetic energy. So because of that force, work is done. See, because of the force, there is a displacement, and because there is a displacement because of the force, a work is done. But body starts moving, so it has against the kinetic energy. So work done is converted into kinetic energy. So work done here is equal to kinetic energy. We denote it by E suffix K. And our regular formula is force into displacement, F dx. So for small displacement, the force is F. So the total work done, you have to integrate. Then Newton's second law, the force is dp by dt, rate of change of momentum. See, rate of change of momentum is equal to impressed force, Newton's second law. So F is dp by dt. But P is mv, mass into velocity. P is a momentum, mass into velocity. So now here, dx by dt is a velocity. So we have replaced dx by dt as v. Now we have to differentiate this mv. But here, in the theory of relativity, mass is not constant. Mass is also, since the body is moving, there is a velocity. So the mass will be variable. So both are variable quantities, mass as well as velocity. So that's why it's a derivative of the product mdv plus vdm. See, mdv plus vdm. Then open the bracket, distribute this integral over the two terms, integral of mv dv plus integral of v square dm. So this is the kinetic energy, integral of mv dv plus integral of v square dm. Now we have to evaluate this. Now to evaluate this, so this is what we have derived, ek equal to integral of mv dv plus integral of v square dm. Now we want to find out this dm. So to evaluate this, we will find out what is this dm and what is dm, what is dv, that we will find. To find out dm, we take the expression for relativistic mass, m equal to m naught divided by root of 1 minus v square by c square. It is same as m naught divided by 1 minus v square by c square raised to half. You take that in the numerator, that plus half become minus half. And now differentiate with respect to velocity, dm by dv. See, dm by dv you find out. Differentiate with respect to velocity. M naught is constant. Now derivative of this bracket is the power. Power comes as a multiple. Then the power of that bracket reduces by 1. So minus half, minus 1, that is minus 3 by 2. Into derivative of what is there inside the bracket. We are differentiating this term. 1 minus v square by c square raised to minus half. So power comes as a multiple. Then the power reduces by 1. Minus half, minus 1 become minus 3 by 2. And derivative of what is there inside the bracket. Derivative of 1 is 0 with respect to v. Derivative of minus v square by c square is minus. 1 by c square is constant. Derivative of v square is 2v. This is what we will get. Then minus minus become plus. 2 and 2 cancels. And what you get here is v by c square. 1 minus v square by c square raised to minus 3 by 2. Then m naught v by c square, we take it common. Then 1 minus v square by c square raised to minus 3 by 2 will go down as 1 minus v square by c square raised to plus 3 by 2. Now we will split this plus 3 by 2 as half plus 1. Law of indices we are using. Raised to half, raised to 1. And it is here. This we now try to separate that. See, this is what we have found here. So we will bring that m naught v and this 1 minus v square by c square raised to half as root of 1 minus v square by c square, because we know that m naught by root of this is nothing but m. So we try to separate it, and what remains there here in the denominator is 1 minus v square by c square. Then you take out that c square outside. This c square you take it here, then take the c square inside. What do you get is c square, and here in second term c square cancels, you will get minus v square. So now here m naught by root of 1 minus v square by c square is m into v by c square minus v square, and we will cross multiply. So this dm into c square minus v square equal to mv dv, and this is what we wanted, mv dv. We write in terms of dm. To simplify that integral, so this integral 1, equation 1. So mv dv, see mv dv equal to dm c square minus v square. So here we substitute, see mv dv, integral of mv dv is integral dm c square minus v square. We substitute here, then open the bracket, distribute it. So c square minus v square plus v square. So v square and v square is constant, and then what remains there is c square dm. C square is constant, comes out as a multiple, and integral of m naught to m dm, m naught to m dm, because see it has started from the rest. So initial mass was m naught, and afterwards at the end of that the mass becomes m. So c square comes out, integral of dm is m, lower limit is m naught and upper limit is m, because lower limit is at the start and m is at after certain time t. Then substitute upper limit m, substitute lower limit m naught, and what you get here is, when you open the bracket, mc square minus m naught c square. Okay. So now ek, we write, take this m naught c square on the left hand side, ek plus m naught c square equal to mc square. So ek is the kinetic energy. Ek is the kinetic energy. So when the body is moving, Ek is the kinetic energy. It is moving the. But what happened? Because of that mass, it also has the energy. See, because of the mass, it also has energy. So before it starts moving, the mass was m naught. So its energy must have been m naught c square. M naught c square was the energy when it was at rest. It is called the rest mass energy, m naught c square. So when the body is moving, that because of the mass, energy remains. Beside that, since it is moving, it is a kinetic energy. So it is the kinetic energy plus m naught c square. That is the total energy. So here equal to mc square. So mc square must be total energy. So total energy is equal to mc square. So this is the Einstein energy mass relation, E equal to mc square. So mass can be converted into the energy. So E equal to mc square means a given mass is converted into energy. M naught c square is a rest mass energy. Now this, in fact, any energy we obtain, whether it is a chemical energy or nuclear energy, the energy is obtained at the expense of the mass. Mass is converted into the energy. So whether it is a chemical reaction or a nuclear reaction, the energy which is released, suppose some heat is generated, so energy is released. Now from where that energy, because energy cannot be simply created, so here energy is converted from the mass. So this E equal to mc square tells us mass can be converted into the energy. The other way also is possible, but it is not coming under this relativity. Energy also can be converted into the mass. Example, a photon can be converted into the two charges of the opposite sign. Two charges means it is converted into the mass. So that is a different, that is the opposite phenomena. From the energy, you can also get the mass. So in fact, from the photon, you can go get electron-positron pair. Okay. So mass can be obtained, but that is altogether different concept. So E equal to mc, this is the energy mass relation. So E equal to mc square. Now we will try to find the relation between energy and the momentum. So take this relativistic mass, simplify this. Take this on this side, square this, open the bracket here, and here we will get m square c raised to 4 minus m square v square c square equal to m naught square c raised to 4. This is the second last line. Then we write this as mc square whole square minus mv whole square c square m naught c square whole square. Now that mc square, see this last equation here, mc square is the total energy. So it is E square, mc square whole square, so E square. Then mv, the body of the mass moving the velocity v, mv, that is the momentum. So mv whole square is the momentum of that body, that is p. So p square, c square, and this is what is m naught c square is the rest mass energy. We write it as E naught whole square. So E naught square. So another way of writing it is E square equal E naught square plus p square c square, and E square equal to this form is often used. E square equal to m naught square c raised to 4 plus p c square. Maybe you might have used this relation, E square equal to m naught square c raised to 4 plus p square c square. You know what is called the Compton's effect. You have studied the Compton's effect maybe in the second year. You might have used this relation, E square equal to m naught square c raised to 4 plus p square c square, to get that what is called the Compton shift. So that is, this you might have already used in your lower standard when you are studying the Compton's effect. So this is the standard relation which is used. So E square, now this is a rest, this contains the rest, this equation is that E is the total energy, m naught c square is the rest mass energy, and this Pc square, that Pc is the energy in terms of momentum because of the motion. Then let us consider the photon. According to the electromagnetic theory, the light is transmitted by means of the wave. According to the quantum theory, the light is transmitted by means of the photon. So now these photons has no mass, but it has a momentum. That's why they are called as the particles. See, the photons, it is called the particle nature. You might have come across that in the photoelectric effect and also Compton's effect. The photon is a particle nature. What is the meaning of particle nature? See, photon has a no mass, but it has a momentum. Although it has no mass, it has a momentum. So that's why it has a particle-like property. So it is called as a particle. It is not called as a particle, but it has a particle nature. Now to get the mass of the photon, see, mass of the photon, m equal, we'll use the relativistic equation. M naught, m is the mass when it is moving, m naught when it is at rest, divided by this. So m naught equal to m root of 1 minus v square by c square. Now photon is the light is made of the photon. So velocity of the light is c. So when the light is transmitted, so photons are moving with the velocity c. So v equal to c. So if you put v equal to c, see, if you put v equal to c, so this becomes 1. 1 minus 1 is 0. So m naught is 0. So the rest mass of the photon is 0. See, rest mass of the photon is 0. Rest mass of the photon is 0 means that photon does not exist. So if the photon is there, it will move with the velocity c. So it cannot come to rest at all. Photon cannot come to rest at all. You cannot hold the photon, because moment if you try to hold the photon, the mass of that will become equal to 0. That means it will not exist. Then this E equal to mc square, you can find out equivalent mass, m equal to E by c square. See, this is the equivalent mass. See, what happens is, this electromagnetic radiation or a photon, they exert the pressure. They exert the pressure. Exert pressure means they exert a force on the surface. They exert the force because of the momentum. It has no mass because of the momentum. Now, this is the only the mass we are finding here is only the imaginary. Imaginary means, suppose it had mass, what it would have been. That's what we are doing. It has a momentum. It has no mass as such, but it exerts the force and pressure. So that is because of momentum and not because of the mass. But suppose if it had mass, what would have been equal mass? So we find it from the energy, m equal to E by c square, E equal to h nu, the energy of the photon. Then nu is c by lambda, so it is h by c lambda. Then momentum of the photon is m into c, m into c. It is m is h nu by h nu by c square, h nu by c square. So what you get is c and c cancel, h nu by c. So this is the momentum, h nu by c. See, actually the moment of the photon is never in terms of the MC. It is given in terms of h nu by c, in terms of the energy, because the photon does not have the mass as such. But in order to get the value of that momentum, we have used here what mass it would have been if it had mass, what it would have been. By using the energy we have found it, or momentum we have found it. So the momentum of the photon h nu by, again this you might have used when you have studied the competence effect. Momentum of the photon, you have considered X-ray as a photon. Momentum of the photon h nu by c. You might have used this. Moment of the photon is h nu by c. Then that E square equal to E naught square plus T square C square. This expression you might have used to find out what is called as competence shift. So it was used there. So with this, we have completed with this E equal to mc square. Okay, we have found E equal to mc square, and also we have found the expression for the mass. So I'll stop here and continue tomorrow.